about localization, actually. So localization, but with a bit special way to do localization using manifold learning. So I'll try to give some brief introduction to what is manifold learning, and then we'll check how we apply to localization of speakers, one speaker for now. And this is a joint work with my student, Rachel Goldstein, and my former student, Ronen Talmon, who is a professor at Technion now. So maybe it's a waste of time to explain what is localization for this audience, but still to have us all in the same on the same level. So actually, there are speakers in an environment. The environment should be reflective environment, meaning that there are a lot of reflections from the rooms, from the facets, from the tables, from the furniture. And we would like to localize the speaker, for instance, in order to direct a camera towards the speaker when he talks, or some surveillance, or as a prerequisite before beamforming and so on. So we have a lot of application. The robot audition is very trendy application nowadays. So the robot would like to come towards the speaker and maybe to have some interaction with him. So for this we need to localize. This has been a problem, open problem for many years. A lot of solutions, a lot of very good solutions, but we try to take a bit different path. Why is it a challenging problem? So localization was actually also used for many years before it was applied to speech processing, for instance in radar application, communication, and so on. So why is it so challenging for the acoustic environment? The main issue here is this multipass regime, and for speech processing it's very severe. So when I talk to you, you actually hear me via a very long constant function, or very long impulse response in the time domain. The impulse response can be in a room like this, few thousand taps. So this is a very major obstacle for localizing. Sometimes, maybe for the people in the back row, the direct pass, which bears the direction, is actually not as strong as the other reflection. So this is why we have to take into account the entire set of reflection in order to localize, or just get rid of these reflections in order to localize the speech signal. Indeed, many of the solutions try to get rid of all the reflections and somehow enhance or emphasize the first arrival. We will try to take a different path, which I will explain later. For the impulse response, it's actually, as I said, multiple reflections from all room facets and all the furniture, but there are some good models. However, they are very complicated models. So there are statistical models by Pollack, Schroeder, and there is also, when I talk to you, first of all, you hear me directly, and then for some close reflection, and then very remote reflection, which we call reverberation usually, or the late part of the reverberation. It will be a very long tail, very unstructured, and we need a statistical model for this. Usually we use a statistical model of white noise with an amplitude that is decaying exponentially with a rate related to the reverberation time of the room. But there are also some deterministic models. However, what is common to all of these models is the fact that they are very, very complicated. Very, very complicated, perhaps too complicated in order to take into account while deriving algorithms. In general, as I said before, I can use the localization as a prerequisite before beamforming. But beamforming, the traditional beamforming, used to use only the direct path. What we encountered already several years ago is that the fact that if you take into account the entire reverberation regime, or maybe large part of the reflections, then you can have much better solutions for the impulse response. So this gives us an incentive. Why do we want to use the entire impulse response rather than only the first part? Although the first part would be, or the direct path will be the natural choice, we think, and we actually demonstrated in several works, that the entire propagation path gives a lot more information that can be utilized in order to apply beamforming, to apply speech processing in general. So as we said, this is a really a tough problem to model the impulse response, also to estimate the impulse response. And this is why we try to result in this work, or this line of works, in data-driven approaches. So the approaches will take some samples. I will explain which sample. It will be a semi-supervised approach, and we will try to take this semi-supervised approach in order to localize the signal based on data rather than based on specific model. So as I said before, just to summarize, many of the works, or maybe many of the traditional works, took into account only the TDOA. This is some type of trivialization that we all know. This is too simplified. We can take the entire impulse response. This is an example of the impulse response, direct path on area reflection in green, and very, very long tail. This is very nice, however, not so simple. And this is why we would like to have some intermediate solution, which we describe here, and it's related to the manifold learning paradigm, and it will try to merge the simplicity of the solutions that are here with a more complicated description of the impulse responses. So this is what we try to do. Hopefully, by the end of the talk, we're really convinced that it's at least something to think about. So the main claim is that if we have an impulse response, it is controlled by multiple parameters. Of course, the room dimension, the duration time, so how much reflection I can have, where the microphone are positioned, where the source is positioned. All of these parameters will have a major influence, of course, on the impulse response that we see here. What we say as a main claim, that if everything is static, and then the only thing that is changing is the position of the speaker, then the only control parameter that controls all the differences between the set of impulse responses will be related to the position, since all other terms or all other parameters are fixed. So this will be the main claim, and another claim is that we can extract this by using manifold learning approaches. So this is what I will try to do today. And more or less along this line, first I will try to convince you that indeed we have a manifold. So the impulse responses, which are, as I said, very, very long impulse responses, or very, very long vectors in our linear space, these are confined to a manifold. So they cannot do whatever they want. They have to be somewhere on a manifold. Then we'll, after hopefully being convinced that this is the case, we will utilize this in order to localize, first by two microphones, to localize only the angle, and then with multiple microphones to actually localize the coordinates of the speaker. So this is what we'll try to do. At the end, I will have some perspective and some new results that I will not have time to describe, but at least to let you know that they exist. So let's start with the data model. These are two microphones. So I start with the problem of two microphones. So I have the speech signal, specifically my speech, and it undergoes this reflection pattern or the impulse response, A1 and A2, towards the microphones. If I have two microphones, so they both receive the same signal, but with different impulse responses. And on top of this, we have noise. So this one bears all the information that I'm interested in. However, if I look at Y1 and Y2, they are heavily influenced by the speech signal, but the speech signal is actually a nuisance parameter, a nuisance variable for the localization. So I can say many things on the same location. It doesn't say anything about one location. So I would like to get rid of the independence on the speech signal. For this, we introduced the relative transfer function. We already did it in 2001. But the relative transfer function is nothing but the ratio between the transfer functions. So A2 divided by A1. That's all. Here there is an example of impulse response So, and we can see some interesting properties. First of all, it peaks. If the elevation level is not too high, it peaks actually in a position which is related to the TDOA, which is fine. But it has also some reflection pattern. However, this reflection pattern is usually not as severe as the reflection pattern of the impulse responses due to the fact that the microphones are a bit close to each other. Another property that we see, which is not a nice property but still exists, is the fact that it's a non-causal filter. So we have, if this is the main response, we have a response even before. We sometimes call it pre-echo. This can be a bit of a nuisance while applying beamforming, but it's not a problem for the localization. This is actually due to the fact that A1 is a non-minimum phase filter, and it's in the denominator, so it might have poles outside the unit circle. But this is not really important. And as we said, now that we got rid of the speech signal, so now we actually only have a feature vector that depends on all these parameters, but specifically the main parameter which we are interested in, and the main parameter which will control my impulse responses or my relative impulse responses will be the source position if everything else remains the same. We have a lot of solutions by now for estimating the relative transfer function. You can imagine something very simple, which is just a cross spectrum divided by the auto spectrum. If it is a noiseless problem, there is no problem to estimate it. Otherwise, we have a lot of methods. Some are listed here, but there are many more, which can estimate the relative transfer function in noisy environment. Please note that the estimation of the relative transfer function is a non-blind problem. So it only relies on the two microphone signals, Y1 and Y2, and does not rely on knowing the speech signal, since the speech signal is cancelled out. So this is a very good property that it can be non-blindly estimated. It is a bias estimated, but we can get rid of this as well. And after doing this, it's not the topic of my talk today. After we did it, we take this relative transfer function between microphone 1 and microphone 2 for D frequencies, and this is our feature vector. It can be very long, can be 1,000 long. So this will be my vector space, which I would like to estimate. So it is a very high dimensional, and as we said before, it is controlled by a limited set of parameters, specifically if there are many of them and all of them relate to the same constellation of microphones in the same room, then the only difference between them, or the only controlling parameter, will be the impulse response. So these are vectors in a very high dimension, and we know that vectors in very high dimension tend to be far from each other if they are not very close. Since it's something somewhat referred to, sometimes referred to as the curse of dimensionality. So if something is very long, in a very long vector, and we'd like to calculate the Euclidean distance between these vectors, if they are very close to each other, there's no problem. But if they are a bit further away, then the distance between them is actually meaningless. So this is why we need to find another way to measure differences between the impulse responses and to utilize it in order to localize. What we claim is that all these very long vectors actually relies on a manifold. We imagine like a carpet flying in the room, so it's two-dimensional, although the room is three-dimensional. Of course, I cannot, this is only three-dimensional, I cannot do this for 1,000 dimensions. It will be a bit more complicated to wave my hands for this. But if we take this three-dimensional problem, we actually say that all these vectors are two-dimensional vectors which lie on a non-flat carpet that is floating somehow in the space. Still, if we look at small patches, as you are depicted here, these small patches we can maintain linearity. However, there is no linear relation when we go across this flying carpet. For instance, if an ant would like to go from here to here, it should obey the all the curvatures of this manifold in order to measure how long she had to walk. Okay, so now we would like to define three affinity measures, or three distance measures. The Euclidean distance, which we all know, some regular dimensionality reduction measure, the PCA, and the diffusion distance, which we'll introduce now. So the Euclidean distance is very simple, just the norm of the difference. They actually are not obeying anything about the non-flatness of this manifold, and they just connect them by a straight line. If you take the PCA, it's a very known dimensionality reduction measure, which is also assuming that everything is flat, and this is not something that we want to do. And what we would like to do is what is called the diffusion map, which is nothing but a discretization of a diffusion process on the manifold. So what do I mean by this? First, we define a measure, which is the Euclidean measure plugged into a kernel, a Gaussian kernel, for instance, but can be another. And all the vertex of this graph will be our RTF vector, and the distances are this Kij. And this epsilon will be a notion of somehow the neighborhood of my RTF. And then we define the diffusion, so actually the probability to go from Hi to Hj, from two nodes. This will become from this. This will come from this normalization, and then we take the eigenvector of this graph, and we have a set of eigenvectors and eigenvalues. These are a representation or embedding of my very high dimensional vector in a low dimensional vector as depicted here. And what we claim that these vectors are well organized, so we can measure the distance between them and sort them according to their distance. Another thing which is good to know is the fact that if we want to calculate the diffusion distance, now I define the diffusion distance, it's actually Hi and Hj are close to each other if they have a lot of paths in between them, a lot of these R's between them. So this is a notion of proximity, and this can be calculated in the Euclidean distance in the embedding. This is an important attribute due to Koifman-Lafont. Just a depiction of what we are doing here. So we have these two balloons with a lot of points. We have A, B, and C. Euclidean distance between A, B, and B and C seems more or less the same. However, there are many passes between B and C, since they are in the same balloon, but A and B should go via this very, very narrow tunnel, and then this is why they have only few passes. So this means that A and B are very remote from each other, and B and C are very close to each other, although from a Euclidean perspective they are the same. So we have these three measures, and let's see which one of them fits better our data. So for this we did the further simulation study. So we have an object, we have two microphones, we have an object. This will be the starting point 10 degrees, and the object can be, or the source can be on this arc from 10 to 16 degrees. And this one is 2 meters. So we measure the distances. We measure, for several variation level, we measure the distances between each point and 10 degrees. And what we see here is, if we look with maybe the green and the red are better depiction, so the green and red are a bit higher variation level. And then we see that the distance, if we take the Euclidean distance, we see that the distance is linear, but after a while it saturates. So after a while we cannot distinguish if 40 degrees or 50 degrees are more remote, which one of them is more remote for 10 degrees. So then the distance becomes meaningless. Same for PCA, although the PCA can extend a bit more this linearity regime. Everything is correct unless the ovation level is very low. If the ovation is very low, this is fine, but usually this is not the case. Here it's maybe 1.7 seconds, so it's much higher ovation level. So you can see that these measures are not good. But if we look at the diffusion distance, we can see that it's almost linear. Well, it's not perfectly linear, but it's almost linear. And then we can utilize it in order to localize, or in order to distinguish between distances. What is also interesting that if we look at this embedding, this one vector, here I localize only one parameter, the angle. If I do this, I see one-to-one correspondence, more or less, between the angle and my eigenvector, which means that I actually revealed the correct parameter that controls the plot. So how do we utilize this in order, so hopefully we are convinced that we have a manifold. How do we utilize it in order to localize? So first we would like to argue, it's quite well known, that localization is stuff. This we all know by now. And if we would like to do a data-driven approach, meaning that we need training, it will be a very cumbersome task to collect a lot of data points, to measure all these points exactly within a specific room. This is why we would like to resort to semi-supervised learning, meaning that we have both labeled and unlabeled training points. The unlabeled training points will reveal the structure of the manifold. For instance, these are unlabeled points. If we look at the unlabeled points, we know that we are on the circle will separate between them. But if we don't know, we can, with these two labeled points, we can have the boundary between the two clusters, which will be very wrong from the real clustering. So knowing the unlabeled data can give you a lot of information. So the unlabeled data will reveal the structure or the curvature of the manifold, while the labeled data will give us encode in order to really localize. So let's define what do we have here. We have labeled data with their labels, we have unlabeled data, these are two of them, and we have a test data. Let's think about how do we measure distances. So we have three terms. The first term is actually the correspondence between our label data and their label. So this one is actually how good our data fits, our label data fits itself. It can be a bit, it's not zero, due to the fact that we might have a bit of measurement noise when we measure the label data. However, if we take this into account, we have what we usually call overfitting. So we try to fit to all points, which is actually not the case, since we assume that everything is much smoother. So in order to apply smoothness constraint, we do two things. The first thing is quite regular Tikhonov regularization, which actually limits the norm of our function. Now it gives us not as good fit, but much more smooth curvature. But what will be very important for us is what we call the manifold regularization. This is what I would like to elaborate a bit. I don't have time to elaborate too much, but if you're interested, we can discuss later. So we can show that in this manifold, after discretizing the manifold with our graph, we can have this second order term as the distance, as the manifold regularization term, and it actually gives us this weight, which is related to the weight that we defined on a kernel. And if the weight is very high, so meaning that they should be very close, there will be a big punishment for F not mapping these points of vicinity to close position. If W is low from the kernel, then we don't care that the positions are off. So only if they are very close under the kernel, then we would ask that our mapping F to be very close, that this position will be very close. So close proximity in the high dimension should reflect in proximity in the low dimension, which is the coordinates of the signal. So this is what we have here. There is something that is called representation theorem, which is actually related, very closely related to the Fourier transform. These are coefficients, Fourier series. This is the coefficient, and these are the kernel. In Fourier, it's a regular exponential kernel. So f of h, rather than a regular, an arbitrary function, we use only this, using the data points, we use only this series expansion in order to solve the problem. When we do this, we actually have a second order equation which can be easily solved, and we find these A star which are the coefficient of our label. So this will give us the solution of f of h. This is called RKHS, the reproducing kernel Hilbert space. Okay, so what do we do here to summarize the main idea? So we have here labeled and unlabeled data. We calculate actually this mapping function under the RKHS approximation, and we have at the end of this we have the weighting A, which actually are representing. This is why it is called representative theorem. It represents the function f, or the mapping function f. Whenever we have a new test sample, which of course we don't know where it is, but we know that it's in the same environment, then we calculate its affinity to all label data, which is depicted here, and using this coefficient that we already learned, we know how to estimate the position. What is interesting is that after localizing a new test point, it can be another unlabeled data. Of course, we don't know its label, but it can be an unlabeled data for the next step, since it's data from the manifold. So if it's correctly estimated, then it's another data which can go back to our training, and then we can adapt the system. We do this until we have enough points. We usually, if you think about it, we live in the same environment all the time. We live in our home, we live in our office. This is most of the time that we spend. So after a while, we have a lot of data from these environments, which can be utilized in order to improve our estimation, and eventually you don't have to update anymore. So we do some adaptation when we start working in a specific environment, and then we stop. Let's see if this is doing something, but before this, I will have a Bayesian perspective, which is actually not far from our perspective till now. So if this was a cost function, and since we have two regularization terms, we mix them together into one normalization term, localization, one normalization term, which is, we denoted the Hilbert space under the kernel K tilde, which is a bit different, different kernel, and this will induce a Gaussian with specifically this term. This one will be the likelihood function, how good the label data is explained, and this will be a prior which is related to what we learned from the data. We will use this perspective later. If we have this Gaussian model, then it's very easy to calculate the map or the MMSE estimator by actually using this Gaussian and calculating the conditional expectation. So these one are the covariance matrices between the label data and our new test point, which is induced by this K tilde. And this one is just the noise of the measurement data, and these are the labels of the data. So it's a solution that we can utilize in order to estimate the position of a test bed. We did our experiments in our acoustic lab. So this one is a bit dark, but this is the acoustic lab. This acoustic lab can control the vibration level. So all the facets of the room is covered with a lot of panels, two-sided panels. One of them absorbing, another one is reflecting. And then if we flip them, we can change the vibration level from around 0.1 second to about 1 second. So it's quite a large range of vibration level, which allows us to measure or to test our algorithm in a variety of environments. The room itself is 6 by 6 and 2.4 meters. So we have our microphone here. Everything is sampled by this box. 64 microphone in, 48 loudspeaker out. Here we use only 2. And we did our real experiment in this lab. It's real but controlled. So our source was allowed to move only, this is the manifold in a sense, was allowed to move only on the line. And there were two microphones, 20 centimeters apart and 2.5 meters from the trace of the speaker. And the speaker can be somewhere. And we would like to see if we can localize. We used only 5 label data on this meter, so 20 centimeters apart from each other. And we would like to test how good we can localize. We compared this with, we used also 30 random test samples on this line in order to have a bit of statistics. So we use it also with noise, so we played bubble noise from the loudspeaker or switch on the air conditioner. So it's other types of noise. And we tested the GCC, which is very commonly used, and you can see that it's not working very well since it's noisy environment and reverberant. And if we look at the nearest neighbor, which the nearest neighbors in a sense can be a good idea, since the nearest neighbor is telling us how close we are to our training point, we have 5 of them on 1 meter. So maybe by doing this it will be okay. So we see this. However, we go beyond this by using this manifold element, since we know the curvature of the manifold. I will demonstrate this again soon. Another thing which is important is how many label data do we need. So of course, if we increase the number of label data, first of all, we improve. The nearest neighbor becomes fine after we have enough label data, and I will explain why. And another thing is what happens with the unlabeled data. So whenever we have more unlabeled data, we can see that we can also improve, since we have a better notion of the manifold or the curvature of the manifold. So unlabeled data helps us. Just to understand why the nearest neighbor is not working, the nearest neighbor is not working due to what we actually said before. The nearest neighbor is nothing but Euclidean distance between our test point and the training point. And since if they are too far from each other, linearity is not preserved. So it becomes non-linear. So this is why 3 meters and 2 meters seems more or less the same distance from my origin. However, if we take our estimator, which is actually using the manifold to regularize the correspondence and finding this function f, we see that it's very, very linear, maybe until the end. Here it's a bit off the linearity, but it's quite linear. So this is why we can use this mapping in order to localize in much better way. What will happen if we have more than 2 microphones, or let's say we have more nodes? For instance, our cellular phones. If we have the cellular phones, please keep them static. I don't know how to solve the problem when they move yet. But each one of them is equipped with 2, 3, 4, depending on your brand, microphones. So there are nice nodes for localizing. And if all of them together, we can localize better, and also we can find X, Y, Z. So actually, we have to see that for each microphone pair, we have the same problem that we had before, as we see here. However, each microphone pair will have another set of impulse responses due to the microphone position. So if this is the case, I actually have multiple viewpoints of the same environment. Each one of them will induce a different manifold, and I would like to somehow merge them. So I have all of these manifolds. Each one of them is related to a specific pair. They actually, all of them, try to reflect the same position. However, they have their own terms in order to do this, due to the fact that they have different reflection patterns and they are in a different position. They might be closer to the wall, they have a different angle, there might be other objects, so they have a different point of view of the same problem, and we need to know how to merge them somehow. By the way, we didn't try this, but maybe it can be also used for a different modality. So another modality that can benefit from manifold learning, video for instance, although video probably the reflection pattern is very simple. But some other modality can be used here as well, since it will be a general technique in order to merge some manifolds. Okay, so how do we do this? This is FHI, so we concatenate all points of view, so all RTFs of our measured position, and we would like to fuse all manifold into one combined manifold which can be mapped to the position. Here I wrote R, but it can be at most R3, meaning that we have X, Y, Z coordinates. So these are the manifolds. Let's have a look at what is happening here. So I have manifold 1, 2, till manifold n. So we see all these manifolds. We define an average process. It's not an average of the localization results, which I will discuss later. It's actually an average of the process that we define, and each one of them will be its own process. Now, we would like to measure distances, since the distances under the kernel induces everything that we know about our localizer. How do we do this? If we measure distances on the same manifold, we already know. So this is easy. We did it under the kernel. We also will do the same stuff here. However, how do we measure distances between one manifold to another? Since both of them live in a different world. Both of them have different set of vectors on their manifold. So how can we compare them? For this, we actually use a very simple methodology, saying that if we would like to measure the distance between this yellow point and this blue point, we actually use the distance to all the training points, all the labeled training points, which are depicted by HI here. But we know that HI1 and HI2 are actually different depiction of the same position. So in a sense, the position here between these sheets, between this manifold, is 0. So in order to calculate the distance between this point and this point, we calculate this to the red point here, reflect it to the red point here, which doesn't cost anything, and then calculate the distance here. And this we do for all label data, for each manifold. So this is the second one, and then we go all the way via all these manifolds to the last one, calculate the distances to all labeled data, since it's the only data that we have, and we have actually at the end we have something like this. So there will be green distances within the manifold and red distances within the second manifold, as you see here. So these greens and these are red. And 1 over m squared, due to the fact that our average process was 1 over m, and we have this new covariance matrix, which is a combined matrix of all nodes. And again, we can apply the same Bayesian perspective. I don't want to get into too much detail. And actually it's the same formula, but now the kernel or the distance measure of the covariances are different, and they are based on the entire set of manifold rather than one root. This is just to show that we can do this. We plot this. So in general we have M processor, each one of them for each manifold. We can combine them together, and we have a test point for which we use this the same equation that we have for the map estimator, and we have an estimate. Again, a new real experiment, so the same room, but now it's a two-dimensional problem. So I have, these are the nodes. We have 3 nodes, as you see here. Each one of them is 20 centimeters apart, and we have these braining points 70 centimeters apart on this area of 2.8 times 2.1 meters. We don't want to get too close to the board. So we have this here, and we want to localize somewhere in the manifold. We actually tested also, I do not show it here, but we tested also if we go a bit beyond the manifold, what is happening if we are beyond the borders of our confined area. So it's still working for a while, but if you're really off this area, then you don't have enough information anymore. So let's compare our result with different results. So first of all, as a baseline, we use the SRPP hat, which is actually a multi-channel extension of the GCC. This is very commonly used in localization, and this is what happens with this. Sorry, it's this one, the purple one. And now we have 2 other methods which are related to our previous method. First of all, we localize. This is what we call here the blue one. We localize by each node and then average the results. This is what happens with the blue one. And another thing is that since we have a kernel, we can multiply all kernels by each other. It's a different method of calculating this K tilde. And this one is the red one. But what we presented, this average process for Gaussian processes, this is the green one. And we can calculate that this distance is much lower than what we can have for the nearest neighbor, which, as I remind you, it was a square of 0.7, 0.7. So the maximum distance for the nearest neighbor is square root of 0.7 plus 0.12 divided by 2. So this is much smaller. This is time to summarize. So hopefully I have convinced you that there is a manifold. That's maybe the main idea. And then if we have a manifold, then we can utilize it in order to localize it, in order to actually regularize our estimator of a mapping between a very, very complicated impulse response to the position. I remind you that if you look at the impulse response, it's a bit crazy, very, very long, maybe 1,000 taps. And the location, what we say, is embedded there, but what we want is to extract or to map this very crazy vector into a coordinate, which is XYZ. So hopefully you are convinced that this indeed exists. We say that it's practical, almost practical, I would say, since you have to measure a bit labeled data, but if you have these measurements, then you can indeed localize in your specific environment. Many people are working on related topics. This is a short list of this. Several extensions, challenges and extensions that we already have. So first challenge, which we already have some solution, is if the speaker is moving. So again, the sensors are not moving, however the speaker is moving, free to move. Then we need tracking. Rather than localization, we need tracking. We have proposed in a conference in a journal paper, a recent one, a tracking method which actually use this manifold localization in order to build a Kalman filter. or extended camel filter, and its variance is related to the distances which are induced by the manifold. This, we have some results already. And what will happen if there are multiple speakers speaking concurrently? I don't know. Hopefully we can solve it. I don't know yet how to do this. Beamforming. Beamforming is a bit more complicated. This localization is a mapping between a very long impulse response into 3 coordinates, x, y, z. However, beamforming is a mapping between multiple noisy signals into one clean signal. So it's much more complicated one. We try to do something about this. This is a preliminary work that I did with Romain several years ago, in which we actually learned some dictionary of impulse responses, and then we projected them, the real one, the one that was measured in the room, we projected it to this library or dictionary of impulse responses. This is still only preliminary study, and hopefully we will be able to work on this as well. So this concludes my talk for now, and I'm happy to have some comments and questions.
Thank you so much.
I'm curious about how you would select the proximity region of the kernel manifold, the epsilon here,
Yeah.
how sensitive it would be for this choice.
It depends on many things. So if your points are very sparse, and then if epsilon is too small, then nothing is connected. And if it's too large, then everything is connected, which is still not good. So we had in the paper some method in order to iteratively estimate this epsilon until we have a reasonable number of points in the neighborhood.
So you add more points.
Yeah, you can think about saying that select epsilon until you'll have 5 points in a neighborhood. It can be something, but we did something a bit more sophisticated.
Can you use the same idea to track the manifold if you have moving sensors? So, I mean, that would be you said that if you have moving sensors, you have an issue, right? But the manifold will change slowly.
Yeah. What we already tried is if the sensors don't move together, but one of the sensors is moving, then the algorithm will automatically track that something went wrong. So it can get rid of it somehow and continue with the others. And maybe try to re-estimate everything, but it's quite preliminary. But it's also limited in the fact that I allow one sensor to move at a time, not all of them together, because otherwise it becomes a bit messy, everything. I'm not sure that I have a good solution for this by now. This is the way that we started. So to gradually reduce the number of nodes. It's, perhaps after we localize, I don't know exactly how to do this, but just a vague idea that after we localize, we have some encode in the point, in the room, and we might use it in order to back localize the sensor by some type of back-to-organization somehow. But it's still vague, open for ideas.
In your first experiment, where you had, I think, 5 labeled data along a line, and you had the unlabeled data along the same line, you got some results.
Mm.
Do you have a feeling what would happen if you were not restricted to this line, if you had more, like throughout the room, labeled data throughout the room, and also more unlabeled data, what would happen to the performance?
Yeah, we actually did it for the second experiment, actually. For this experiment, we also tried, one of the reviewers asked us, so we also tried that the test point would be outside of this rectangular region. And if it was not too far, then it had enough information. But then, so you can say that it's some envelope around, like a map that you put on a table. So a bit beyond, it's still okay, but not too far. So I don't recall exactly the details. It's in the paper, but if we went like 50 centimeters out of this region in which we learned, we still were okay.
So you would not say that increasing the number of labeled data would impact the precision negatively?
No, I don't think so. It's actually, if you have enough labeled data, then go to US paper, it will do again, and you don't, you have to finish my talk. Sorry, if you have enough labeled data, then you're okay with Euclidean distance. Because everything, you always find some close labeled data. However, we claim that this is a tedious task. Since labeled data, you really have to go with a ruler and measure a lot of things. So you prefer not to do it too much. But unlabeled data comes for free. So whenever you stay in the environment, you have unlabeled data. So whenever people are wandering around in the room, it's fine. Of course, if there is like a point in the room which I never visited, I don't know, a lot of dust, so then I don't have enough points there. So I need more points, but the unlabeled data will reveal the structure of the manifold. The labeled data is expensive, so this is why we try to avoid labeled data as much as we can. We need something in order to anchor our flying carpet, otherwise it will fly somewhere.
Could you have a single manifold instead of multiple ones in the case, and then have the pair between the source and the
So higher dimension.
Yeah, I mean, like right now you have multiple. Your microcomposition is set, right?
Yeah.
And is that and your source position is on a grid or whatever.
Yeah.
But then you could have both positions in the learning phase.
Yeah,
I don't know if it makes sense.
I think it makes sense. It's actually, we more or less did something like this. What I called this, sorry, I'm in the wrong direction. Since you say, let's concatenate the vector, and this will be our manifold. It's actually saying that each one of them is independent depiction, and we have to multiply the probability density function. So this is what we did here in what I call kernel mult. So then this is a long vector. Well, either you have a very long vector and then you do everything together, or you did for each node separately and then you multiply the result. This is more or less what you want to do, and it's not as good. You can also learn, but this I think would not be a good practice, but you can learn everything with just, you say, I have multiple vectors, let's concatenate them in a long vector and learn the mapping for this long vector to my XYZ. I think it's not good, actually also related to the previous question, since if one of the manifolds is off or not functioning anymore, you took yourself on and left the room. So I have less vectors, so then you'll have, in your method, I have to learn everything from scratch. In my method, I just say, okay, rather than averaging 5, I would average 4, it's still working. So the fact that I have a specific mapping for each node, it's a more refined built-in block in order to have the localization than to have all of them in one go. So I think it's better to keep it separate.